Hello? Is that okay? Thank you for your attention. My name is Stephen Cartwright. I'm a master's student at the University of Calgary, and I'm going to describe our immersive application for optimizing well placement for reservoir engineering. First, I'm going to give you a little bit of background. Then I'm going to describe our application. Then I'm going to report on some of the outcomes from our feedback session with subject matter experts. Oil and gas can be recovered in a number of different ways. One common technique is to inject fluids down an injector well. This creates pressure and pushes the petroleum products such as oil and gas up through another well called a producer. The job of the reservoir engineer is to determine the optimal well placement to create a recovery scenario that is economic and safe. They do this by looking at several different well placement scenarios and then running computer simulations. And then they pick the best simulation. However, simulation time can be very long, so your candidate solutions are they need to be chosen wisely. Our tool is designed to help people pick good well placement scenarios. It's not always easy to determine what is a good well placement scenario. It requires a lot of understanding of the fluid flow and the geological structure under the earth. As you can see here, there's a lot of factors that can affect this. For instance, with different layers, there can be a lot of different properties of the rock, or as we call it, the porous media, that can affect the fluid flow. Plus, geological features such as faults can make it very difficult to understand how the fluid is moving through the subsurface. And this is, as I said, very important to picking these good scenarios. There's a lot of data that goes into building a reservoir model. It comes from things like seismic data, well data, a variety of different sources. But then it's all blended together mathematically to create a probabilistic representation of the subsurface. This subsurface representation is then discretized into grid cells. Each grid cell has various properties that can affect fluid flow, and it has to be able to represent geological phenomena such as faults and discontinuities. So this is what this all looks like. So you have a complicated 3D data set, and you're trying to put three-dimensional structures into this data. It can be quite hairy at times, so the reservoir engineers need all the tools that they can get. So one technique that we're using to help the reservoir engineers is connectivity analysis. Connectivity relates to how well fluid flows between different grid cells, different parts of the reservoir. And we can actually model this as a mathematical graph. So a grid cell would be a node, and then with the edge weighting of transmissibility, which is how readily fluid flows between different grid cells. Then we can run algorithms such as Dijkstra's shortest path and find out where fluid flows most readily. We built a two-dimensional tool to do this. However, we found that it was necessary to keep changing the view quite often, and we had to rely a lot on the other analysis panels to find a good solution. And it could sometimes take a fair bit of time. So we decided to try building an immersive version. So why did we decide to build an immersive version? Well, with we're looking at these connected volumes to a well. It's a three-dimensional volume, and we're trying to fit it into this complex three-dimensional data. Also, you're trying to understand how the three-dimensional volume of one well, drainage volume of one well, interacts with the three-dimensional drainage volume of another well. There's a lot of things that can benefit from increased spatial perception here. Additionally, the wide field of view is quite useful because you can conceptualize what's happening in a large scenario at once. And the increased field of regard is quite beneficial as well because you can reduce the information clutter because you can move information and data around and have different areas where you can work on it. Also, another benefit is you can have much more natural interaction. So if you want to just turn your head to look around a well, that could be a quite nice method to interact with the data. We implemented this on a couple different platforms, a Cave and an Oculus Rift, and we also implemented it on the Oculus with a Gamepad and a Leap Motion controller. And the idea here is to have an application that runs on a variety of platforms so that we can leverage the benefits of each platform. And for instance, the Cave, we bring a lot of groups through our visualization center, and when we have a co-located group of people, they quite like being able to see it up in a big visualization space. However, the Oculus Rift is, of course, much cheaper and much more widely available and portable. We wanted to try a Gamepad because people are very familiar with it. It's a very standard tool. But we also wanted to see how receptive our users would be to using gestures for this kind of work. All the interaction techniques were implemented on both the Cave and the Oculus with the Gamepad. So this includes menuing system, basic manipulations, like your scaling and your translation and rotation, well trajectory, like putting in the wells, either vertical or freeform, and then, of course, the connectivity analysis tasks. All of this was implemented in the Cave and the Oculus with the Gamepad. With the Leap Motion, we wanted to kind of test the waters and see how the users would, if they would accept using gestures. So we only built a few things on the Leap Motion. So here, for example, in our Cave is our menuing system. Just a very basic menu. Press a button, menu comes up. Use array to select different things. For instance, a filtering operation. Scaling, translation, rotation, just button controls on the Gamepad. For the cell probing, you got to remember we have this complex 3D data set. So we actually have, you press a button and the array turns into a three-dimensional cursor with a transparency bubble around it. And then you can actually probe into the data set. So you can scan the surface, but then using the transparency bubble, you can actually probe into the reservoir as well and find cells within it. But so that you can have a good context and understand what cells you're interacting with, we still maintain a wireframe of the cells. And then once you're in there, and you can also probe cells and wells and perforations in the well. And you can also get a data panel that comes up whenever you're probing, and that gives you all your different properties for those grid cells that are so important to understand. So here's an example of the probing at work. As you can see, there's the transparency lens, and then you can probe in and around. Well placement, vertical well placement, quite simple. You just take the ray, find a spot on the top of the current data set, and then press a button, drops a well in. Freeform well placement is much like probing. You press a button and you get your 3D cursor, then you can just walk around and perforate wherever you want. The perforations where you make a hole in the well, and that's where it interacts with the media. So then you go around and you can perforate, and that defines your well trajectory. And it also gives you the data so you can find good candidate blocks for perforation. And then once you've done that, as you can see there and here, you get a nice freeform well. And here's a few of us doing that in the Cave. In terms of the analysis, so once you've put your well and you want to analyze the placement, you can look at this graph here. Like I said, this is a mathematical graph representing the drainage volume. And you can actually, and also the color represents how connected. So there's also a color ramp here to give you an indication of how well connected each of the cells are. And you can actually filter that out too. So you can apply a threshold. So if you want to find extremely well connected cells only, then you can set a threshold that is desirable for your application and just see that. And here you can see probing, analyzing the cells around the, like in the graph, to find out what properties are affecting the connectivity. And then you can also select the connectivity based on the perforation. Those green balls are perforations, or the wells. And here's the filtering. As you can see, you just do a slider, and it adjusts that threshold. We also have panels providing quantitative data. For example, hydrocarbon pore volume is quite an important stat, as one example that's on there. And that's for instance, all the like the volume available for hydrocarbons in the connected volume that you're analyzing. And you can see how nice it is to have this large workspace to work in, because you can lay out your panels and all over and stack them and zoom and blow them up and shrink them and organize them however you like, and users seem to quite like that. Also, I should mention that when you apply the threshold, that is also updates the panels. So not only does the visualization change, but the data changes. So you can see the stats for both the well without the threshold applied and with the threshold applied, and that can help you find a good threshold. All the features were also implemented on the Oculus Rift DK2, tracked with the Vicon system. As you can see here, there's the probing with the transparency lens. And then I think she's going to go do some connectivity analysis here. Probing to find out what properties are affecting the connectivity. For the Leap Motion, we have a little bit of a different menu system. As you open your hand towards your face, the menu appears, and then you can use your other hand to select things. Here's an example of a filtering operation at work. Scaling, translation, and rotation, 3 different gestures, so scaling, translation, rotation. One thing I will mention is we actually applied a speed threshold, so you have to move fast enough to trigger the action and to prevent accidental triggering of the action. And then also to reduce fatigue, if you want to perform like an action, you just have to do it once, and then it'll keep doing it as long as you keep your hand in front of the sensor. As soon as you drop it out of the range of the sensor, then it'll stop the action. And this prevents you from having to keep panning and moving your hands around all the time. Cell probing is very similar to with the Gamepad. So then you can just take your hand and you just probe the cells. Here's an example of that. Much like the 3D cursor. So as I mentioned, we didn't do a formal user study, but we did put this in front of some subject matter experts. We had six people participate in our feedback sessions from a variety of different ages and sexes. All of them had both undergraduate and graduate degrees in petroleum engineering. 5 out of the 6 had professional work experience as a reservoir engineer. So we'd bring them in, we'd give them a questionnaire to determine that they were suitable subject matter experts. We'd explain the tool, what we were trying to achieve, give them a run through, and then we'd spend the next 60 to 90 minutes going through the application and recording their feedback and what they thought of the application, the different platforms, and the different user interfaces. So for the application, all of them reported that they found the connectivity analysis quite useful for their work. They actually did find the increased spatial awareness quite beneficial for these kind of tasks. They quite liked being able to move between different platforms. They thought that was a useful thing, because then they could work at their desk but then bring an application into a larger visualization center for more collaborative work. And what else? Yes, oh, they really liked they liked being able to work with engineering. They liked being able to work with the engineering data in this way, with these kind of controls. They found it was very engaging and a nice way to work with the data. So regarding the cave versus the Oculus, they really did appreciate working together and being able to see each other and have an interpersonal conversation while viewing the data. Unfortunately, only one head is tracked, so it's not perfect. But they did say for general collaboration, it was probably good enough a lot of the time, but that's definitely a weakness. They also really liked the wide field of view. It was really nice to walk in there and see the whole reservoir laid out. And they found that with the Oculus Rift, at times it was almost too immersive. So they were too immersed in the reservoir, whereas being out in the cave, it was actually quite nice. But they did say that it was nice to be able to sit at their desk and use an Oculus Rift, so perhaps they would prefer to use that for either solo work or remote collaboration. With regards to the Gamepad versus the Leap Motion, they really liked the idea of using their hands to interact with the data. They got it instantly in terms of the concept. They were apprehensive, however, about learning gestures. Perhaps surprisingly, they actually seemed to find the Gamepad more intuitive in the sense that they would have to remember the gestures and that kind of thing. So, but perhaps if they had time to become more familiar with it and learn the gestures, then that would be overcome. And one thing that came up is they found the Gamepad they felt like it was more precise. And it turns out being precise and having rock-solid interaction with the data for these kind of scientific and engineering applications is very, very important. So they perceived the Gamepad as more precise, so that pulled them towards the Gamepad. Another thing that came up was they really liked working between near and far data, and they felt that the Gamepad was better for that, perhaps because it has a ray and the cursor's further out, so they could work between the near and far. When you're using the hands and getting in there, touching the data, it's really good, but they felt like they were always a little bit closer than they wanted to be. Yeah. Some comments. So in terms of further investigation, features to better support co-located collaboration. I know there's a lot of things out there with regards to remote collaboration and avatars, but what if you want to have a group of people work together? What's the best way to do that? In the same spot, consistent UI between different platforms. The users were really excited about being able to move between a large scale and a small scale environment, but only if it was very, very simple, and they wouldn't have to learn or experience. They wouldn't tolerate a whole bunch of different user interface paradigms in the different platforms. And making sure that we're getting natural interactions that still support the need for precision and the need for that near-far kind of work that they desire. Questions?
Okay, so we can take a short question. One. Yes.
So this is great work, and I really applaud how much effort you clearly put into developing the application. We just don't see that many very, elaborately developed VR simulations. And I wonder, since it's been done so well, if you have any idea right now whether or not people will prefer to use this new interface over the previous implementation on the desktop, and for what reasons?
Yeah, so we're actually looking at moving. One of the reasons we want to build this out is we would like to develop a tool where people can come in and do this, and we can collect more and more information about this. So we want people to do exactly what you're saying, prefer it over their desktop. And the comments were, yes, I mean, it could be. Like right now we have, I mean, it's fairly well built out, but it's not a commercial product, right? So it's prototype-esque, right? So they said they would use it if the data formats were well supported, if it was easy to bring data in and out. That's one of the biggest barriers. They said if we had that, then they would probably come, and especially because we have this connectivity tool that's fairly unique as well. So between the immersion and the connectivity tool, and the natural interfaces, then there's enough there that some of them said they actually would if we built more features and more support. And, yeah.
Have you used the other interface stuff?
Oh yeah. 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 You're welcome.
Okay, so let's thank our speaker again. And this is the end of this session.